All right, let's talk about something that's all around us all the time, but we can't actually see it. It's this invisible force that cooks our food. It drives our weather. It's the reason the sun feels warm on your face. We're talking about heat, and we're going to break down exactly how it works.
So, let's start with something you've probably experienced 100 times. You stick a perfectly cool metal spoon into a hot bowl of soup, and just a minute later, the handle is almost too hot to hold. What's going on there? How does the heat get from the soup all the way up the handle?
Okay, now let's scale that up a bit. Think about sitting around a bonfire. You can feel its warmth from feet away. Or even crazier, think about the sun. It's warming the entire planet from 93 million miles away, across the total emptiness of space. So clearly there's more than one way for heat to get from one place to another, and that's what we're going to dig into.
But before we can get into how heat moves, we've got to nail down what it actually is. And honestly, this is where a lot of us get things a little bit mixed up. So let's clear up a really common point of confusion.
So here's the big one: heat versus temperature. We tend to use those words like they're the same thing, but in physics, they are completely different. Temperature is a measure of how fast an object's atoms are moving or vibrating. Think of it like a speedometer for particles. Heat, on the other hand, is the transfer of that energy. It's the actual flow of energy from a warmer spot to a cooler spot. So you can think of it like this: temperature is a state, but heat is energy on the move. And what happens when that energy transfer finally stops? Well, that's when we reach a state called thermal equilibrium. It's a fundamental rule of the universe. Heat will always flow from a hot object to a cold one until they've evened out and reached the exact same temperature. At that point, the transfer stops. The ice pack example is perfect. Your warm body transfers heat to the cold pack until you both just feel cool. You've reached equilibrium.
Okay, so we've established that heat is energy in motion. But how does it travel? What are its transportation methods? Well, it turns out heat has three main ways of getting from point A to point B.
First up, we have conduction. And this is the answer to our spoon mystery. When the tip of the spoon gets hot, its particles start vibrating like crazy. They then bump into the particles next to them, which makes them start vibrating, and they bump into their neighbors, and so on. It's basically a chain reaction of jiggling atoms, passing energy all the way up the handle. It's heat transfer by direct contact.
Method number 2 is convection. This one happens in fluids, so liquids and gases. Just imagine that pot of water on the stove. The water at the very bottom heats up first, right? When it gets hot, it expands, becomes less dense, and starts to rise. At the same time, the cooler, denser water from the top sinks down to take its place, gets heated up, and then it rises too. This creates a powerful circular flow called a convection current.
And finally, our third method, radiation. This is how you feel the heat from a bonfire without touching it. It's the transfer of heat through electromagnetic waves, mostly infrared radiation, which is a type of light our eyes can't see. And here's the really important part. Unlike conduction or convection, radiation doesn't need any particles or any medium at all to travel through.
Yeah, that's the truly mind-blowing part. It can travel through a complete vacuum. It's the only one of the three that can do this. It's how all of the sun's energy gets to us here on Earth. Without radiation, our planet would just be a cold, lifeless rock floating in space.
Now, these principles aren't just for our kitchens. They are operating on a massive planetary scale. In fact, they are the engine driving our global weather systems. And one of the absolute best examples happens every single day along pretty much any coastline in the world.
This is a perfect large-scale example of convection. During the day, land heats up much faster than water. So the hot air over the land rises, this creates a low-pressure area, and the cooler, denser air from over the sea rushes in to fill that space. We call that a sea breeze. Then at night, the whole thing reverses. The land cools down faster than the sea, so now the air over the warmer water rises, and the cool air from the land moves out to replace it. That's a land breeze, a giant, natural convection engine just doing its thing day after day.
So all this vibrating and moving around has another really fascinating effect. We've seen what it does in fluids, but what about in the solid? Well, when you have billions and billions of particles all vibrating faster and pushing against each other, the entire object actually expands. It gets just a little bit bigger, and this has some huge implications in the real world.
I bet you've seen this 1,000 times without even thinking about it. Those small, deliberate gaps between the sections of a railway track, they're not a mistake or a flaw in the design. They are a critical piece of engineering, and they're there for one reason: heat. On a blazing hot summer day, those long steel rails soak up the sun's energy and they expand. They actually get longer.
Now, if there were no gaps, the rails would have nowhere to go. They'd slam into each other with incredible force and would eventually bend and buckle. And that, as you can imagine, would be a disaster for any train. So those gaps are simply expansion joints, giving the metal room to breathe.
And you can actually use this trick at home. The next time you have a jar with a metal lid that just won't budge, try running the lid under hot water for a few seconds. The metal lid will heat up and expand just a tiny bit more than the glass jar, and that's usually all it takes to break the seal. A little everyday physics to the rescue. Okay, so once we understood all these principles, we got really smart about putting them to work for us. We've learned how to control the flow of heat by carefully choosing materials that either let it pass through easily or stop it dead in its tracks.
And it really all comes down to two kinds of materials. On one hand, you have conductors. These let heat travel through them super easily. Think of the metal in a cooking pan. On the other hand, you have insulators. These do the exact opposite. They slow the flow of heat way, way down, like the plastic or wooden handle on that same pan.
And once you know about this, you start seeing it everywhere. Your oven mitt is a classic insulator, designed to stop heat from reaching your hand. A thermos is an amazing insulator, using a vacuum to stop both conduction and convection and keep your drink hot for hours. But then you have a thermometer, which relies on a good conductor. The liquid inside has to absorb or lose heat quickly so it can expand or contract and give you an accurate reading.
So when you really look, you can see heat's invisible hand everywhere, from the jiggling atoms in a spoon to the giant convection cycles that create our weather. It's a fundamental force that's constantly shaping our world. So now that you know the secrets behind this invisible force, how does it change the way you see the world?